Have you ever looked up at a massive airliner soaring through the sky? Those colossal machines that defy gravity, and genuinely wondered, how do they make that giant thing turn? Or slow down with such pinpoint precision for a landing? Ah. Today we're taking a deep dive into the very heart of that question. Aircraft flight control systems. Welcome to the deep dive, where we take your source material and extract the most important nuggets of knowledge, giving you a shortcut to being truly well-informed. Our mission today is custom-tailored for you, especially if you're a student diligently preparing for those challenging ATPL theory exams. We're going to distill crucial concepts, emphasize the key knowledge points that frequently appear, and arm you with the insights you'll need to confidently approach, and conquer those exam questions.
Exactly. And we've taken a comprehensive look at excerpts from Aircraft Flight Control Systems, a truly foundational text for anyone in aviation, really. We're going to explore the intricate mechanisms, the essential checks that keep these systems safe, and the critical devices that enable such precise control and ensure, well, unparalleled safety in the skies. This deep dive isn't just about definitions. It will provide a robust understanding, going beyond the what to explain the why behind these systems. Understanding the design philosophy is absolutely vital for that deeper comprehension required for professional pilot exams.
Okay, let's unpack this fascinating puzzle right from the start. When a pilot moves the controls in the cockpit, say, the control column by the rudder pedals, how does that relatively small human action translate into a massive wing flap moving or the tail fin swinging on a multi-ton aircraft? It can't just be a simple pull of a rope, can it? There has to be some serious engineering at play to transmit that initial human input to the actual control surface.
You're hitting on the core of it immediately. That translation from pilot input to aerodynamic effect is achieved through three primary methods. Each has distinct characteristics, often chosen based on the aircraft's size, speed, and design philosophy. And understanding these differences is fundamental for your exams. First, we have the mechanically operated system. This is the most direct method, and you'll commonly find it in lighter, smaller aircraft. Imagine it like a direct bicycle brake cable, but, on a much grander scale. The control surfaces are connected directly to the cockpit controls via a literal physical linkage, a system of cables, rods, levers, and chains. So if a pilot pulls the control column rearward, that action directly pulls on cables, which in turn causes the elevator to move upward. What's crucial here is that this direct connection means the pilot physically feels the aerodynamic forces on the control surfaces. They get a very intuitive sense of the air loads acting on the aircraft. It's simple, robust, and incredibly reliable for aircraft where the forces required to move the surfaces aren't, well, immense.
So in that system, if you're flying fast, the stick gets heavy because you're actually feeling the direct air pressure on the control surface.
Exactly. You'd feel that increased resistance, giving you direct feedback on your airspeed and how much force you're exerting against the air. But as aircraft got larger and faster, those aerodynamic forces became huge, immense. Trying to move a giant rudder against a high-speed airflow with just muscular strength became, well, impossible. That's where hydraulic power comes in. For larger aircraft, immense forces are needed to move those substantial control surfaces. Think about trying to move a barn door with your bare hands versus using a powerful hydraulic ram. It's that level of force multiplication we're talking about. In a hydraulic system, the pilot's physical input might still move a control column, but that movement doesn't directly shift the control surface. Instead, it opens a control valve that directs high-pressure hydraulic fluid to an actuator, which then does the heavy lifting to move the flapper rudder. This effectively decouples the pilot's physical effort from the massive force required at the surface, enabling much larger aircraft designs and higher operating speeds.
That makes perfect sense for heavy lifting. But I know modern aircraft, like airliners, have something even more advanced, right? Like a digital system.
You're thinking of electrically operated systems, often known as fly-by-wire. This is the most modern approach and a significant leap in complexity and capability. In a fly-by-wire system, the movement of the cockpit control doesn't create a mechanical link, nor does it directly open a...
All right. Many thanks for listening to this free part of the ATPL Theory podcast. If you want to continue learning and access the full comprehensive guide, go to my Patreon at patreon.com/ATPLtheory or my Hero at herohero.co/ATPL. That is patreon.com/ATPLtheory or herohero.co/ATPL. Wishing you all the best.